Okay, so now we're going to look at an example of actually solving a differential equation. So in the last video, we did the exercise of verifying that a given formula is in fact a solution of a particular differential equation. This time, we're going to start with the differential equation, and we're going to see how to come up with this formula in the first place. So this is an example of solving what's called a separable ODE. And so we will see that again in a little while. It's not too important for the moment. I just want to give an example of how to solve a differential equation to point out some of the features involved. We'll look at solution techniques coming up soon. So let's see. Let's find the solution of this differential equation. So I'm going to write it as dy dx equals minus 2xy. And then I'm going to do something that looks completely fishy. And I'm going to move the y to the left side. Okay, well, that's not completely fishy. But I'm going to move the dx to the right side by multiplying. And that part is kind of fishy. So I have dy over y equals minus 2x dx. And then I'm going to brazenly integrate both sides. And so on the left, we're going to get the log of absolute value of y plus some constant. And on the right side, we're going to get minus x squared plus some other constant. And then let's see. Well, I don't actually need to have two arbitrary constants here. I can subtract the C1 over to the other side, and then I can call this entire thing right here my new constant, C. So I can actually just rewrite this as log absolute value of y equals minus x squared plus some constant C. And now I'm still trying to solve for y, so I will exponentiate both sides as follows. And let's see what happens. So on the left side, the e and the log cancel because those are inverse functions. So I just have absolute value of y is equal to, and then on the right side here, this splits as e to the minus x squared e to the c by using the exponential rule. And then since this here is itself just an arbitrary constant, I'm going to replace that just by c. And now I have c e to the minus x squared. And now since this is an absolute value, that means that y is equal to plus or minus some constant times e to the minus x squared. But again, remember, that is just some constant. So I'm going to take this whole thing here, since this is just some arbitrary constant, I'm going to call that now my arbitrary constant c. And so this is going to look like c e to the minus x squared. And at this point, you should be throwing your hands in the air and saying, what the heck? How can you do that? So we've gone through using c in different successive lines in different with different meanings all the way through. Yeah, sorry folks, that's just how it works in differential equations. It's an arbitrary constant, so we just update it as we go along. This is called abuse of notation, sort of an unfortunate term, but there you go. Once you get used to it, it actually makes a lot of sense. The first time you see it, it looks dreadfully like cheating. But we'll see that it actually just simplifies things greatly, and it boils down to being the same thing, because when you're given an equation with an initial condition, substituting in will give you the same answer regardless. So one other thing, though, that looked like pretty fishy is what happened back here in this step. Well, actually, what I did right here is I was integrating 1 over y times, and then dy dx dx. That's really what this notation right here stands for. So even though it looks fishy, this is just a handy mnemonic. It's a shortcut, um, because it avoids having to do the chain rule, which would allow you to convert this into that form and then integrate just the way I did. So it's a time saver. Okay, so now let's look at some observations from what we've obtained here. So first off, the solution is a function. So just as was mentioned back in the very, very first lecture, the solution is a function. It's not a number. So this is different from what you're used to from algebra or calculus. And so it has to satisfy the differential equation for all values of the independent variable x. Secondly, we notice that the differential equation is solved by integrating. That's how it is. We want to get rid of those derivatives, and we get rid of derivatives by integrating. Another important feature is that constants of integration appear during the solution process and need to be kept. They are essential. And fourthly, the presence of this arbitrary constant c means that you have a one parameter family of solutions. And so c is that parameter. It can take all sorts of values. And so, in fact, you don't just have one solution here with this formula. This is actually a whole family of solutions. And we'll explore what that means more when we look at the next video.